All right. Thank you so much for organizing this COVID paper session. It's really nice to be here in person again to talk about this. Hello everyone. I'm Knut Anders. I am a PhD student at the University of Bergen, and I'm presenting some joint work with Mikhail Balash and Jaakko Järvi. We are at a research group. Let's see. Yeah. We're at a research group which explores new ways to develop complicated behaviors in graphical user interfaces. So in this project, we look at how one can perform structural changes, such as swapping elements in a list, or inserting elements, or removing elements in what's called constraint system-based GUIs. And this is difficult when you have some data flows going on between these elements, because now you need to update this data flow. You need to update the connections between these elements when you start swapping things around, moving elements around in your structure. And oftentimes we experience GUIs where these types of operations are missing, even though it would be very useful to the user. So I hope I can show you today that this does not have to be that difficult for the programmer to implement. And our solution is a domain-specific language for doing this. So in this domain-specific language, you can specify relations between your elements, and using these relations, you can specify your operations. So before I explain the approach we did, I want to spend a few minutes explaining what constraint systems are and why constraint systems matters in GUIs. So for those of you who have done any type of GUI programming, you're probably aware that there are different GUI architectures. So you have model view controller, model view model, and these, just to mention a few. And these architectures, they try to separate the model from the view, where the view is what the user sees and interacts with, and then the model is your underlying data and the business model of your application. And with this separation, you can write event handler code, which will modify properties of your model, and then you can attach these event handlers to GUI widgets, such as buttons and sliders and text bit inputs and so on. So here, for instance, if we want if you want these buttons, clicking these buttons to increment and decrement this number, you will specify this number as a property of your model. Then you write event handler code, which will increment and decrement this property, and then you attach these event handlers to the buttons. This works perfectly fine when these event handlers are simply modifying single properties of the model. But a problem arises when you have some sort of relations between your widgets, relations between your model properties. So now your event handlers, they can no longer just update this single property. They actually have to update all the properties that are related to this property, and those related to these properties again, and so on. So here, for instance, is a dialog box for resizing an image. You will typically find this dialog box in photo or image editing softwares like Photoshop. And to resize the image, you can type in the height or width in pixels, or you might want to do this relatively to the initial width and height, so that you can specify that I want my image to be twice as large, or 1.5 times as large, for instance. And also a check button to say that I want to preserve the ratio of the image. So here there are several, we can think of several relations. For instance, one would be between the absolute height and absolute width and the ratio. Another relation here we want to maintain will be between the relative height, relative width, and the ratio. And there is a few more. And the point is that in all the event listeners here, so the event listeners for each of these text fields, you will have event handlers, event handler code, which will have to maintain these relations. And the code for maintaining these relations, they are different between each in each of the event handlers. And there are other aspects which makes handling relations maintaining relations in event handlers bad. So for instance, if you want to have multi-way data flow in your GUI, or you want to have asynchronous computations, which is very common to have in GUIs. So I won't go into these aspects now, but please come and talk to me in the break if you are interested in those things. But the point here is that maintaining relations in event handlers is bad. So we propose a different model for doing this. Yeah, just to illustrate here, here's the how the different event handlers interact with the different properties of the model. And it should be clear from this image that this is really tedious and error-prone to write this event handler code yourself. Just a second here. Yeah, we propose a different programming model where you specify all the variables of your GUI components and relations between these variables in one place. And with each relation, you specify a set of methods to enforce that relation. So in our library called WarmDrink, you can we call these relations constraints, and together they make up a constraint system. So to demonstrate how you can use this with a resized dialog box example, here we have a constraint system specification of the logic of the dialog box. So here are a couple of variables, the properties of the model, and here are some constraints on those relations. So this is, for instance, the constraint on the relative height, relative width, and the ratio. And with this specification, we can now bind widgets in the view to these variables. And when the user updates these variables through the view, then a constraint system solver will find what it considers to be the best way to update propagate this update to the rest of the variables in such a way that all the constraints are enforced. So this is all good and nice, but what when you start introducing structures into your GUIs, which is very common. So structures such as lists or grids or trees. So I'll use an example throughout the rest of the talk. So here is a GUI for planning a conference. So we have talks here, and you can think of each talk as one GUI component. And it should be clear that there will be some internal relations going on inside the component. There will also be some relations between components. And the most obvious one here will be that the start time of one talk should be equal to the start time of the previous talk plus the duration. And this is possible in WarmDrink. You can use variable sharing. So one component can store references to another component and then use these references in the constraints. So here, for instance, each talk can store a reference to the variables of the previous talk, and then have a constraint which says that my start time should be equal to the previous talk's start time plus the previous talk's duration. So to show the constraint system specification here, we will see that there are actually two components here. There is an agenda component and a talk component. And just think now that the agenda component will contain many talks. And the interesting thing here is that we have these ampersands, which denotes references. So these references can be used in the constraints here. And these will have to be connected outside of this specification using JavaScript assignments. Just to give the full picture here, we also have some variables in this agenda component, and this is just so we have something for the first talk's references to point at. So imagine now that we have inserted a few talks. Well, first I should say to append the talk at the end now, you will just append this talk in the structure, and then you will assign the references of that talk to the previous talks. And think now that we have, imagine that you have inserted a couple of talks, and now you want to do some structural changes. So start swapping talks in the middle, or removing a talk, removing or inserting talks. And this is a bit tedious to do because now you have to update these references correctly, and it actually matters where in the structure you're doing this. So removing an element in the beginning of your agenda would be different from removing the talk in the middle of the agenda or removing it at the very end. So to simplify developing structural operations, we created a domain-specific language that we call WarmDrink. And this DSL sits on top of your HTML website. So it assumes that you have some constraint components which are connected to some HTML view. And this DSL produces an API which will perform structural operations structural operations on both your model and your view. And there are some relations here to GUI frameworks such as React and Angular, but this is not meant to compete against these. It's not meant to be a GUI framework. Its sole purpose is to add structural operations to websites which use a constraint system under the hood. So in this DSL code, you can write define the structures of your GUI and relations between elements in this structure, and then using these relations, you can specify operations. So I will demonstrate this now. So using the conference app, here we define the structure of this app. It has one agenda, and an agenda has a list of talks, and a talk does not contain any more components. It's simply a talk. And then we add some constraint variables and references, which are the same references that we saw in the specification code earlier. We just expose these here so we can use this later on. So now we can define relations between talks. And in this case, we define the relation proceeds between a talk A and B. So a relation has a test block, which will test whether the relation is established or not, and it will have establish block to establish the relation. And here we see some functions which are in the standard library, but you can also create your own if you want. This is a predicate that will return true if B follows A in the structure. And by the way, these functions, they have full access to the entire structure of your GUI, so you do not have to pass these as arguments. So this will simply check that B follows A in the structure, and this function will insert B into A's container after A. And the interesting part here is these two lines where you, which are assignments. Now we use these references and the variables we defined above. And here in the established part of the relation, we update the constraint system. So now we can finally talk about transformation rules. These are the rules that enables us to implement structural transformations. So a transformation rule has preconditions and postconditions separated by this double arrow here. And as I mentioned earlier, it matters where in the structure you're making the change. So swapping in the beginning of a list is different from swapping in the middle or swapping at the end. So for this particular rule, we are swapping in the middle of the list. So we need some additional context. We need the talk before and after these two talks, which we are swapping, so A and B. And this rule will expect an A, B, C, D order, and then establish an A, C, B, D order. Yeah, swapping B and C, really. And there is nothing complicated going on when executing this rule. It will simply check that all these relations hold, and then it will establish these relations here in order, and then it will check that these relations hold using the test block of these relations. So for this relation here, this will insert C after A and point C references to variables in A, and so on until C and B and C have been swapped. By the way, the checks here, like checking the preconditions and postconditions, this is just to help the programmer and give an error message if something went wrong, and these can be turned off in a production environment. So from this rule, we generate a JavaScript function, and to execute this rule, you simply pass 4 components, 4 subsequent talks to this function. This was only one of the rules we needed though. So here are the rest. We need a rule for swapping at the beginning, swapping at the end, and actually yet another one for swapping 2 talks when there are only 2 talks in your agenda. And here we are introducing some new relations, his first talk in and his last talk. So by the way, we're using infix notation here. You probably saw that in the previous slide. So this is just because it reads a bit better. And this relation here will insert B to be the very first element in this list. And this relation actually has no establish block. It's just there to check that C indeed is the last element in its container. Right, so this is the core part of the DSL, and now I want to explain 2 additional features, which is convenient to the programmer, which is multi-case rules and parameterized rules. So I've just now shown 4 rules for doing swapping, and it would be very convenient. I mean, this will generate 4 different JavaScript functions, and the programmer has to know which of these functions to call in which scenarios. And it would be very convenient if you could just call one function swap, and it will choose the correct operation for doing this. So WarmDrink provides this with what's called multi-case rule. So here we have inserted our 4 transformation rules into a multi-case rule, 1 case for each of the rules. And there's 2 interesting things going on here. So the first one is that when executing this, it will choose the case where all the preconditions hold, and it will execute that particular case as the operation. And we're also deriving some of the arguments here using a XPath-like expression. So for instance, A, we're deriving A, or saying that A is the preceding sibling of B. And if B has no preceding sibling, then A has no value, and all the preconditions that mentions A will fail or will return false. Right, and we also have parameterized rules. So some of your structures you may have several structures in your GUI that have different relations between your elements, but the structures, the operations are actually almost the same. It's just the relations that are different. So for this situation, we have these parameterized rules, which are parameterized over the relations. And since we do not know the types of these relations, we just use the any types for the arguments. So to demonstrate this, let's imagine now that we add more days to our conference. So we have several days, and we want the text of each day to increment by 1 from the previous. And you can do this by having an index variable in each of these day components, and you can store a reference to the previous day, and have a constraint saying that my index should be the previous index plus 1. And then from this you can derive whether to show Monday, Tuesday, Wednesday, and so on. And now we might want to add some structural operations, such as swapping days or inserting a day in between 2 days. And the relations between these days, they are different from the relations between talks, but the operations for swapping and inserting and so on, they are actually the same. So therefore we can use the parameterized rule swap and instantiate it with different relations, and to produce 2 operations, swap talks and swap days. So this was the main part of the DSL, and I will close off now by shortly talk about the IDE for this DSL. So we used, it's implemented with Xtext, which is a language workbench that produces an Eclipse-based IDE. This IDE has all the typical things you would expect from an IDE, like validations, syntax highlighting, quick fixes, refactoring tools. And whenever you save this specification file, it will generate a JavaScript file which contains all the functions for doing your structural operations. So it will generate the API file, which you can simply include in your HTML website. So one of the features of this the IDE is that it will validate parameterized rules. So for this parameterized rules for inserting a talk B or element B in between A and C, we cannot really know here whether these relations are correctly used, because we do not know the types and arities of these relations. But when you instantiate this rule, we will actually have this information. So we will know the types here, and then we can deduce the types of these elements, and the IDE will be able to show the programmer error messages if something is wrong. All right, so hopefully I showed you today that structural changes in graphical user interfaces does not have to be that difficult. And if you're interested in any of these, or just interested in constraint system programming with the GUIs in general, please talk to me after in the break, or just sometime during the conference. Thank you so much for listening.
Any questions?
Yes.
Hello. So why did you have to insert all the cases for the list of swap? It wasn't enough to just say that there is a swap that takes a list of talks before be empty, a talk A and a talk B to swap, and a list of talk after can be empty? Will that cover all the cases already?
What more values?
In order to have a single rule instead of one rule for the various cases,
Yes.
you would just have a rule that takes a list of tags, as you do anyway after, so you clearly can. So a list of tags that appear before, and this list of course can be empty, a tag A and a tag B that are supposed to be swapped, and then the list of tags to have after that again can be empty. That seems to capture all your cases.
Yes, then you will have to know whether this list, this is actually a very good point, and this is perhaps something you could do. One thing we'll have to think of that is that this list might be empty as well, list before and list after, and then you will have different scenarios depending on whether this list is empty or not. You could say that this list perhaps exposes less variables of the last talk and do some interesting things there, so this might be an interesting approach.
So my question is, sort of in your kind of established blocks, you can update the pointers in the example.
Yes.
So one question is, does that mean that the sort of order in which you declare the dependencies actually has a meaning?
Yes, and it actually is. So perhaps it's unfortunate. We have to be very careful about the order of the established blocks or the code collisions in tools. Very structured.
I see. And so just a small follow-up on top of that is then sort of just could you speak a little bit about the way you think this is sort of one of the particular like the benefits of this, because it seems like you also have to reason about these kind of updating references and then such like in a model view controller I might write a functional sort of update that takes my view of my model and sort of updates it, and that might be slightly easier at least in functional programming to reason about. Whereas here I'm sort of reasoning about these pointer references and stuff.
Right, so I guess the functional approach here would be to compute the entire network, which again is that's an interesting approach. So compute the entire network of all the references, and perhaps try diffing this network to the previous network. And this is something we're looking into as well, which is I think might be a future work going on there. Yeah, I think I have it more. So, yeah, so, it's a very good idea.
A little bit related to that, do the cases need to be exhaustive? And is there a way to check whether?
Right now, we have no way to check these. So, the easy thing we did there was just that it checks the cases one by one, and it will report an error message if it gets to the bottom. But it would be very convenient if we could statically analyze these cases and be able to say that now we have some cases that are not covered. But currently, this is not supported.
Thank you. Any other questions? Okay, then we can take the.
Thank you so much.